Let's talk about balancing chemical equations, and I call this the secret revealed. This is something that was very important and still is very important, balancing chemical equations. The chemical reaction is a process in which reactants form products in chemical change. Science has to identify the reactants and products, and we also determine what quantity the reactants form products. We know that that involves the relationship of moles of reactants and products. And we determine the energy considerations of the reaction. Reactions do not create or destroy matter. Atoms are conserved in the process. Therefore, we must have a bookkeeping system that accounts for every mole of atoms, both reactants and products, to make sure that there is the same number on both sides of the equation. The shorthand we use to record all of this is called a chemical equation. Let's talk about the simple reaction of carbon burning in oxygen, carbon like charcoal. Carbon will burn completely in oxygen. That's called complete combustion, and the product is carbon dioxide. Here is the equation. 1 mole of carbon reacts with 1 mole of oxygen to form 1 mole of carbon dioxide. Before the reaction, if we look at it on the atomic and molecular level, you have a carbon atom and an oxygen molecule. Oxygen is diatomic, as you know. After the reaction, the carbon is chemically bonded to the 2 oxygen atoms in a linear molecule. The atoms are the same on both sides. They've just rearranged, but the quantities of atoms are the same. This equation is already balanced, as you see. Now let's look at the properties of a balanced equation. We have the same number of carbons on the left as on the right. We have the same number of oxygen atoms on the left as on the right. It's atoms that balance, not necessarily molecules. The atoms are merely rearranged. Before the reaction, after the reaction, rearranged but the same number. So, take a moment to identify which of these equations is balanced. And, as you see, these equations are balanced and these are not. Here, for instance, we have 1 aluminum on the left and the right, but we have 2 nitrogens on the left and only 1 on the right. And keep in mind, the rule for balancing equation is made so that we conform what happens on our paper to the reality in the lab. You start with a skeleton reaction, that is, you write down the species, reactants and products just as they occur in the laboratory. So, for instance, hydrogen gas reacts with oxygen gas to form water vapor. You may never change a subscript because this changes the character of the species. You can't, for instance, balance this by making this H2O2 because that's no longer water, it's hydrogen peroxide, and you're lying. Then we change the coefficients until the atoms on the left and the right are the same for all elements. So, for example, in water formation, we change the coefficients. Here's our skeleton reaction, as we saw on the previous slide. There are too many oxygens on the left. Therefore, we increase the number of oxygens on the right. What we're always looking for is the not enough. There's not enough oxygens on the right, so we change the coefficient on the right. This balances the oxygen. There's 2 on each side, but there's 4 hydrogens on the right and 2 on the left. There's not enough hydrogens on the left. And so we now multiply the hydrogens by 2, and we have a balanced equation. The same number of atoms of each hydrogen and oxygen on both sides of the equation. Now, if we interpret this visually, before the reaction, we have 2 molecules of hydrogen and 1 of oxygen. After the reaction, we have 2 molecules of water but the number of atoms is still the same. And so there's a song. Atoms on the left equal atoms on the right. They just rearrange, but their mass is always tight. Conservation is the rule, in reactions don't be fooled. Atoms on the left equal atoms on the right. When you balance your equations, write all things in proper stations. Get the arcs right, or you will get no sequel. Then don't touch the lovely subscripts, coefficients, chains, left-right trips. Until left and right, you're sure the atoms equal. Atoms on the left equal atoms on the right. They just rearrange, but their mass is always tight. Conservation is the rule, in reactions don't be fooled. Atoms on the left equal atoms on the right. Lead nitrate dissolves in water, NaI2 as it oughter. Mix them well and you will get a yellow solid. Not 1 microgram will vanish, be your notes in English or Spanish, though it might if your technique is pretty squalid. Atoms on the left equal atoms on the right. They just rearrange, but their mass is always tight. Conservation is the rule, in reactions don't be fooled. Atoms on the left equal atoms on the right. Carbonates react with acids, most times being far from placid, and the effervescence rises from solution. If you lose the CO2, you will see mass decline, a boo-boo. Dump it out and try again, it's not pollution. Atoms on the left equal atoms on the right. They just rearrange, but their mass is always tight. Conservation is the rule, in reactions don't be fooled. Atoms on the left equal atoms on the right. Let's look at sodium reacting with water. We know that this is a very violent reaction, so energy is given off. The skeleton reaction, sodium plus water gives you sodium hydroxide, that turns the water pink, and hydrogen gas. Again, we look for not enough. There's not enough hydrogens on the left. See, we have 1, 2, 3 over here. So we double the amount of water on the left. Now there's not enough oxygen on the right. So we double the sodium hydroxide on the right. Now there's not enough sodiums on the left, but we've balanced the hydrogens too. With not enough sodium, we simply increase the number of sodium moles to 2, and we have a balanced chemical equation. Here's another example with the balanced equation. Notice that sodium has a charge of 0 as an element, as a reactant, but the hydrogen in water is a compound. It's sharing electrons with its oxygen. The product, NaOH, shows sodium with a +1 charge because hydroxide has a -1 charge. So the sodium has lost an electron to become sodium ions. It has been oxidized. And hydrogen, the hydrogen in water, has been reduced to neutral hydrogen gas. So that's a reduction. Sodium is oxidized to sodium ions. Bonded hydrogen in water is reduced to neutral hydrogen gas. Electrons are given off in the oxidation and taken in the reduction. This is an oxidation-reduction reaction. Electrons are lost and gained, and that's what happens in oxidation-reduction reactions. Here's another one. Calcium reacts with hot water to form calcium hydroxide and hydrogen gas. I think you can see this is another oxidation reduction because calcium is changing its oxidation state from 0 on the left to +2 on the right. Now there's not enough hydrogens on the left, so we double the amount of water. Now everything is balanced. Boy, that was fast. What's the difference between this case and the sodium-water case? Well, it's the original formula for the 2 hydroxides. Sodium hydroxide, NaOH, versus calcium hydroxide, CaOH taken twice. Let's go to the oxidation of methane. Methane reacts with oxygen to form carbon dioxide and water. We have more combustion reactions on a separate YouTube video. There's not enough hydrogens now on the right, only 2. So we double the water vapor. Now there's not enough oxygens on the left. So we double the oxygens. Now everything is balanced. Let's read it together. 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water vapor. Now let's see if 2 moles of oxygen, 2 volumes of oxygen with 1 volume of methane is the best ratio, because we can test the conclusion in the lab. And we'll compare it with 2 volumes of methane combined with 1 volume of oxygen. Now, I don't have the equipment to do this on the slides, but when you do in the lab, make sure to cup your ears to protect your hearing. Here's another. This is a very interesting reaction with a stinky gas hydrogen sulfide. Must be done in a fume hood. Silver nitrate reacts with hydrogen sulfide, which of course is hydrosulfuric acid in water, to form silver sulfide and nitric acid. This is called an ion exchange because the silver and the sulfide are swapping from the silver nitrate to the hydrogen sulfide. There's not enough hydrogens on the right here, as you can see, so we double that. There's not enough nitrate now on the left because we've doubled the nitrate on the right. So we double the silver nitrate, and now the reaction is balanced. Here's an acid-base reaction, another kind of ion swap. Sulfurous acid reacting with potassium hydroxide to form water and potassium sulfite. Again, the ions are exchanging partners. There's not enough hydrogen on the right here because we've got 3 on the left. So we increase the water that's produced, and now there's not enough potassium or hydroxide on the left, so we double that. This aqueous belongs over here with the potassium sulfite, and now it's balanced. We can also have this reaction which produces chlorine gas. I think it's fairly easy to see it's an oxidation reduction. There's not enough oxide on the right here, 1 versus 2, and so we double the waters. Now there's not enough hydrogen on the left, 1 versus 4 over here, so we quadruple the moles of hydrogen chloride or hydrochloric acid. And now it's balanced. Now this oxidation reduction is fairly easy to balance, but many oxidation reductions are much harder. Manganese comes in as +4 and leaves as +2, so this is an oxidation reduction. So this sample quiz, rewrite these word equations and balance the chemical equations.